Roll number 4 is there? C, roll number 4. C, roll number 4, Vinayak Jadhav. Okay, so you are not giving attendance. Whenever I am calling your roll number, you was earlier lectures, you were not there. Okay, so if you have any microphone issue, then you should tell in the chat box. But I am never finding your attendance also in the chat box. So here onwards, take care. Roll number 6, 7. It's okay. Here onwards, you have to take care about your attendance, because how would I know that whether you are present or just joining and keeping the mobile aside, right? So you have to take care for your attendance, nothing else. Okay. So 8 participants are there. Still 7 students are absent. Okay, so let us start with the lecture. So just tell me the slides are visible to you or not. The slides are visible?
Yes, ma'am.
Okay. So in yesterday's lecture, we have seen the combined transformations. Combined transformation is done with the help of matrix multiplication. And as matrix multiplication is non-commutative, you have to follow the order of the operation. That is the very important thing for carrying out multiple transformation, right? Multiple or combine. It is also called as combined transformation. So we have seen the rotation about arbitrary point, and we have seen the reflection through arbitrary line. So these two things we have seen how to carry out these transformations using the combined transformation that we have already seen, right? Then we have started with 3D transformations. So the coordinate in 3D is represented with its x, y, z values as specified here. So either you can have 3 rows, 1 column format, or you can have 1 row, 3 column format. Any way you can represent your 3D point. Similarly, homogeneous coordinate system can be represented in similar manner as that of two-dimensional transformations. So there x, y, z as it is, and 1 indicates here overall scaling factor. So either you can write it in 1 column with 4 rows, or you can have 1 row and 4 column here also for homogeneous coordinate system. Then we have seen the coordinate system with right hand and left hand. So if right hand, the 3 first fingers are stretched with 90° to each other, then the thumb represents the x-axis, the forefinger represents y-axis, and the middle finger represents z-axis. If we are taking the left hand, then z is pointing away from the user. That is the difference between these two notations. Then we have seen the combined T transformation matrix, in which the transformation matrix is a 4x4 matrix, where this column indicates the translation along x, y, and z respectively. So tx, ty, tz, these are the three values which are the translating factors along x-axis, y-axis, and z-axis. Then we have seen these three elements are always 0. This one indicates the overall scaling factor, h value, and this 3 by 3 matrix. Whatever we are having here, this 3 by 3 matrix is responsible for all the operations except translation. For translation, we are using this column only. And for remaining transformations, we are using this 3 by 3 box. Out of that, these diagonal elements are responsible for scaling. The off diagonal elements are responsible for shearing, and reflection also we have seen. So for reflection, we are having three cases: reflection with YZ plane, reflection with XZ plane, and reflection with XY plane. So by using these three planes, we are getting the remaining values. Sign is going to be inverted. So if positive x is there, then we are going to get negative, and vice versa. So that is the different T matrices that we have learned. So the 3D translation, this is the T matrix. Remember, it is represented, the 3D point is represented in 4 rows, 1 column. 4 rows, 1 column format. If you are using the horizontal representation, that is 1 row and 4 column, at that time you have to transpose this T matrix also. So that is about translation. So you can see here the new coordinate is achieved by adding tx, ty, tz values in x, y, and z respectively. Then we have seen the 3D rotation. So 3D rotation is carried out with 3 axes: x-axis, y-axis, and z-axis. Rotation about x and z are considered as positive, while the rotation about y-axis is considered as negative rotation. And that's why we are taking the minus theta for that y rotation about y-axis. So this is the T matrix for rotation about x. As the object is moving around x-axis, its distance from the x is going to remain same, and that's why x dash is equal to x. So we are keeping the first column and first row like this. X is getting multiplied by 1 so as to get x dash, and no further addition is required, and that's why remaining 3 elements in column as well as row are 0. Then these 3 elements are already 0. This is 1. These 3 are also 0 because translation is not required here. So only the 4 places are there which we need to fill. So those 4 places are filled with the cos theta, sin theta, cos theta, like that. So as it is a positive rotation about x-axis, that's why minus sign will come here. Theta is the angle of rotation. Okay. Then we have seen about y-axis. So y-axis, in that y dash is equal to y, and that's why the second row, second column will be fixed. And remaining 4 spaces are filled with cos theta, sin theta. Now see here, as the y, the rotation about y-axis is considered as negative, that is in clockwise direction, and that's why here the sin theta are they have changed the replace the places. So that is the difference between y-axis rotation. Then in the z-axis, z remains constant. So you are having x dash and y dash changing, and that's why the third row and third column is fixed, and the 4 elements cos theta sin theta is replaced like this. Remember, for z coordinate, for rotation about z axis, the rotation is anti-clockwise again, considered as positive, and that's why here minus sign comes here. Okay, next 3D scaling we have seen. So as that of 2D scaling, 3D scaling is also of two types. Either we can get the expansion or we can get the compression. If scaling factor Sx, Sy, and Sz, they are greater than 1, then expansion takes place. If less than 1, then compression takes place. And if these three factors are equal, then it is called as uniform scaling. And if these three factors are unequal, that is they differ in values, so it is called as differential or non-uniform scaling. So these diagonal elements are responsible for scaling. Okay, so this is scaling factor along x-axis, this is scaling factor along y-axis, and third is scaling factor along z-axis. Then comes 3D reflection. So 3D reflection is nothing but the mirror image that we have already discussed. The reflection, earlier the reflection was done with x-axis, y-axis, y equal to x, y equal to minus x, for 2D transformation. But in case of 3D transformation, we are going to take the reflection about the planes. So xy plane, yz plane, and xz plane. So we have seen these three T matrices. About yz reflection means x will be changing in its sign. Here the magnitude of the x is not going to change. The distance of this object from the plane, the same amount of distance is there on the other side of the plane. So in short, I can say the distance of this object from the plane, the same distance is followed after reflection also. So that is nothing but the magnitude is not going to change, only the sign is going to change. So sign is changed with the multiplication with -1 here. So -1 and remaining values are 1, 1, 1 in the diagonal. All the diagonal elements of diagonal are already 0. The reflection about xy. So reflection is taken with respect to xy. So z will change its value. The missing term always changes. That only you have to remember. If yz plane is there, missing term is x. So x is changing in its sign. Then xy plane is there. For xy plane, z is missing. That's why z will have -1 multiplying factor. Then comes the xz plane. So in xz plane, y is missing. In xz plane, y is missing, and that's why y will change in its sign. Okay, so that was about reflection. Next is 3D shearing. So till this particular point we have covered, and now we are going to see the shearing effect. One second. Okay, so shearing is done or shearing is possible only due to of diagonal elements. So here the next slide is showing that only. So let us read these points. So 3D sharing, it is a transformation that distorts the shape of the object. So already we have discussed, due to sharing, the shape of the object gets distorted. So it is like shifting the internal layers caused to slide over each other. That is nothing but the sharing. In two-dimensional transformation relative to x-y axis to produce the distortions. In 3 dimension, we have z-axis also. So in 2D, what we have seen, the shear is along x-axis, which is called as shear x factor, and shearing takes place along y-axis, which is called as SHY factor, shearing along y. So this is in case of 2D. Now there is 3D object, and that's why the third shearing is also possible, that is called as shearing along z-axis. So the factor is SHZ. Now, okay. So here we are going to change the shape, and the shape gets distorted. So for that purpose, we will have one example. Let us say a cube is there. Let us say this cube. Now, if the cube is having the length, breadth, and height, obviously it is cube, that's why every side is equal, and I will have that side is equal to 2 centimeter, let us assume, right? Each side of the cube is having the dimensions, having the size as 2. Okay, one of its vertex is origin. One of its vertex is origin. So can you tell me the coordinates of those 8 points? This cube is having total 8 points. If one of the coordinate is origin itself, one of the coordinate is origin itself. So can you tell me the remaining 7 coordinates? Yes. All of you are getting the question? Yes, students. All of you are getting the question? The size of the cube is, or the side length is equal to 2 centimeter. Now, as this is a cube, every side will have length is equal to 2. Every side will have its length equal to 2, right? So can you tell me the coordinates of each and every vertex? So I will draw it here. So what are the coordinates of this? It is your origin, right? So origin is having coordinates 0, 0, 0. So it's x, y, z. All values are 0. I will write here 1. Okay. Then next point is this horizontal, which is lying on x-axis. So can you tell me the coordinates of this point now, which is lying on x-axis? Yes, am I audible? Yes, students.
Yes, ma'am.
Okay, so can you tell me the coordinates of the point which I am representing here with red color? So this side is 2 centimeter. As it is on the x-axis, so its x value will be equal to 2. Its y and z values are 0, 0 because it is lying on x-axis itself. Similarly, this is first, second point. This is third point. Let us see. What can be the coordinates of this point? It is having z value also 2, right? It is 0, 0. From that, I am moving 2 units towards right and 2 units towards z direction. So I will have x value 2, z value 2, but y value is still 0 because it is lying in xz plane. Then this fourth point. Now can you tell me the coordinates of this point? It is along z axis. So x and y coordinates will be 0. X and y are 0 and z value will be 2 and this is your h. So these 4 coordinates are over. Now these above 4 coordinates. So what will be the coordinates of this point?
Ma'am, x and z become 0, ma'am.
Right, very good. X and z, they are 0 and y value is equal to 2. Then for this particular point, it is present in xy plane. बॅक साइड फेस जो आहे तो XY प्लेन मध्ये आहे. त्याची Z व्हॅल्यू काहीच नाही आता त्याच्याकडे. ओनली इट हॅज X and Y values 2, 2. So X and Y values are 2, 2. Z value is not there. This is your H. Next. So 2201 is this point. Then what about this point? It is present in space. It has X value as well as it has Y value and it has also Z value. So all the 3 coordinates are 2, 2, 2 because it is in the space. So it has every coordinate. And here, this point is present in YZ plane. And in YZ plane, the X is 0. So X is 0, Y and Z are 2, 2. Okay, so these are the 8 coordinates. These are the 8 coordinates. Now those 8 coordinates, I am going to multiply it with the shearing factor. Now let us shear it along Z axis. So shearing it along Z axis. So for that, always remember the diagonal elements are 1 in case of shearing and off diagonal elements are non-zero. But here these 3 elements are there for projection purpose. These 3 elements are there for translation purpose. So remaining values we will put. So here I will have some, let us say 3 and 3. So what is the meaning of this? I am having the shearing along Z. third column represents always the Z value. First column represents X value, second column represents Y value, and third represents Z. So these two elements which are off diagonal, they are responsible for shearing, and that's why I am making them as 3. And remaining values I will keep at 0 because I don't want any shear effect along x-axis or along y-axis. I want it along z-axis only. Okay, so that is shear along z. Here it is also same matrix, only transpose is taken. Transpose. Why? Because they are representing this original object with a column. आपण बघितलं होतं 3D मध्ये 3D representationलाच. What they are doing? They are representing the element, one point in the one column format. But what we are taking, we are representing the point horizontally with 1 row and 4 columns. And that's why we have to take the transpose of T matrix also. Right. Now perform this multiplication. Perform the multiplication. This first row and first column. So first row, first column. I will, oh, sorry. I will go to that shearing. Okay. So shearing along z-axis I am carrying out. So perform this multiplication of first row, first column. I actually forgot to make the camera on again. Okay. Okay. So what I'm doing here. Okay. So I am going to multiply this original P matrix with the T matrix. So first row, multiply the first row with first column. And I will write the results here. Okay. So 0 into 1, 0. All these things are 0. So first element that I will be getting is 0. Then first row and second column is also 0. Then first row and third column is also 0. And first row and last column is 1. Obviously, because origin is the first point and origin will not change. That is 0 gets multiplied by anything will be 0 itself. Okay. So that will not change. You will have that point as it is. Next is the second row and first column. So 2 into 1, 2, remaining all zeros. So 2 remains as it is. Then second row, second column, 0. Then second row, third column is 2 into 3, 6. So here it is 0, here it is 6 and 1. Then this row, third row, we will take third row and first column. So 2, then 2, second row, second column is 0, Second row and third column is 2 into 3, 6 plus 2. 6 plus 2 is 8. And this one. Then fourth row, first column is 0. Fourth row, first column is 0. So here remember that x is not going to change. X is not going to change because the first column is as it is. Right? There is no addition. And that's why first column x will be same only. Similarly, y is also same because the second row only one element is present over here, which will multiply only the y value. Otherwise, all the things, there is no addition in this. So we are finding that 0 to 0, that is the only thing I am getting here as x. Similarly, 0 0 0 0 is the thing that I am getting as y, and only there is change in the z coordinate. So when I multiply this fourth row with third column, then I will have 2 into 1 2, and this is 1. Okay, so the next is this row and first column, so it is 0. Then second row, second column, it is 2. Then second this row and third column, so 0 plus 6, so it will be 6 only, and this row with last column equal to 1. Then next column is 2 to 0 1, so 2 multiplied by 1 is 2. This multiplied by second is equal to 2. This multiplied by third column is equal to 2 into 3 6 plus 2 into 3 6 plus 6 12. So here I will be getting 12, here 1, and then next is 2 2 2 1. So 2 as it is, here also 2 as it is, and this multiplied by this is 2 into 3 6 plus 6 12 plus 2 14. This is 14, this is 1, and the last row, this into this is 0. Second row, last row, second column is 2. Then the last row, third column is 6 plus 2 8, and it is 1. So now if you see, the x and y coordinates are not going to change. The whole thing 0 2 2 0 0 2 2 0, we are finding the same results in the first x value 0 2 2 0 0 2 2 0, then 0 0 0 0 and 4 times 2, 4 times 0 and 4 times 2. So x and y are not going to change, only z is changing. Only z is changing, and as only z is changing, you will get the deformation in the shape. It is no longer cube now. आता हा क्यूब आहे का नाहीये, कारण त्याचे x and y parameters are not changing, only z parameter is changing, and that too with differential, that is there is no fixed change. So here if I want to plot the diagram, then it will be like this. So ultimately there is change in the size and shape of the, or there is deformation in the shape and size of the cube. So by making the changes in the z coordinate only, we are getting the distorted image. That's why it is called as shearing along z. Now if I want to have shear along y, then what will be the T matrix in that case? I want shearing along y axis. This is shearing along Z axis. So if I want shear along Y, then these two elements will be non-zero, which are off diagonal elements. हे दोन off diagonal elements आहेत, they will be non-zero for shear along Y axis. And for shear along X, these two elements will be non-zero. Then you will get the shear along X. All of you are getting it?
Yes, ma'am.
Okay. So these are the three types of shearing: shear along X, shear along Y, and shear along Z. So we can have this shearing transformation matrix. In XY plane means along Z. That's why Z parameter is changing. Here it should be 1. Huh? By mistake it is written as here. Here it should be 1. The diagonal elements are compulsory 1, and the off diagonal elements are responsible for shearing. Then XZ plane means Y is changing. So second row will have change. And YZ means X is changing. That's why the first row is having that effect. Okay. Shall we move to the next point? Clear this, all of you? Is it clear?
Yes, ma'am.
Both side?
Yes, ma'am.
Okay. So let us see the next points, which is in general 3D rotations. So meaning is, as we have seen the rotation in 2D also. So the rotation in 2D was carried out with respect to origin only. But later we were able to rotate the object about any arbitrary point in 2D space, right? So, and the procedure was you have to shift that point such that it will coincide on origin. Then you have to carry out the rotation and translate that point back to its original position. So these are the 3 steps for the general rotation of 2-dimensional objects. Now, similarly here also, we are having only 3 cases of rotation. We can carry out rotation along x-axis, rotation along y-axis, and rotation along z-axis. So we are having only 3 T matrices where x and z rotation is considered as positive and y direction rotation is considered as negative. So if only x, y, z axis are given, then only I can rotate the object. But suppose instead of x, y, z, I want to rotate the object about any arbitrary axis. Okay, so this is the axis around which I want to rotate the object. Getting it? So now it is not neither x nor y nor z. It is the arbitrary axis around which I want to rotate this pyramid. Getting it? All of you? Yes. Earlier we have seen the 3D rotation. हे आठवतंय का एक minute? Right? 3D rotation. 3D rotation काय बघितलं होतं आपण? About coordinate axis फक्त 3D rotation बघितलं होतं. Rotation about x-axis, then rotation about y-axis, and rotation about z-axis. So these 3 conditions we have studied. That means we can rotate the object around any coordinate axis only. But what if I have an axis which is not a coordinate, but still I want to rotate that object with that axis? For example, For example, so it is a cube and I want to rotate this cube. Earlier, I can rotate this cube with either x-axis, y-axis or z-axis because I have those T matrices to rotate around them. So easily we can just take the coordinates of the cube and multiply it with that specified T matrix, then we were getting the results. But here my question is, now the axis of rotation is not any of these three. Suppose it is this axis, which is arbitrary axis. And now I want to rotate this cube around this axis. Now it is not rotating around X, or it is not rotating around Y or Z. It is rotating about, suppose, axis L. So it is the L axis around which, whether it is visible to you, whatever I am drawing.
Yes, ma'am.
Okay. So I am rotating this object around this L. Okay. So, but I don't have the matrix for this rotation. Okay. माझ्याकडे कोणते मॅट्रिक्स आहेत आता? फक्त रोटेशन अबाउट एक्स आहे, रोटेशन अबाउट वाय आणि रोटेशन अबाउट झेड आहे. पण मला आता या तिन्ही ऍक्सिस बरोबर रोटेशन नाही करायचं ऑब्जेक्टचं. आय वॉन्ट टू रोटेट दिस क्यूब अराउंड ऍक्सिस एल. Okay. Now there are two cases. One is if any arbitrary axis is parallel to the coordinate axis. मग आता हा arbitrary axis आहे L. If it is parallel with the coordinate axis, so consider this is x-axis and L is parallel to x. Or if I want to rotate the object around this axis, which is your axis M, and this M axis is parallel to y-axis. Or I can have any third axis, which is LMN, suppose, and I want to rotate this cube around N, which is parallel to z-axis. Okay, so first case is this rotation is carried out about any arbitrary axis which is parallel to coordinate axis. So if it is parallel to coordinate axis, then what I can do, I can shift that coordinate axis, shift that arbitrary axis so that it will coincide on the coordinate axis. मग हा L असेल तर तो मी मूव्ह करणार, that will coincide on X. If the axis is M, then I will shift it so that it will coincide on Y. And if the axis is N, then I will shift it down so that it will coincide on Z axis. Okay, because it is parallel. Because it is parallel. So first option is, first thing is translate that axis, that rotation about axis parallel to coordinate axis is there, and so that you have to translate this axis so that it will coincide on the coordinate axis. Then now the L and X are same. L is coinciding on X. So L and X are same, and that's why I can carry out the rotation around X, because I know the T matrix for rotation about X axis. So then I will carry out the rotation with the specified angle theta. That is my second step. So first is translate it down such that it will coincide on X axis. This is your L and X are same. Then perform the rotation of the object around this axis. And third, once the rotation is over, our job is over. We have to carry out only the rotation. So as our job is over, we are going to shift that axis to its original location. So translate inverse. So translate the object, translate the axis, then rotate, and then translate inverse to the original position. These are the 3 steps for rotation about an axis parallel to coordinate axis. Getting it, all of you?
No ma'am, repeat करा.
Okay. What about 3D rotation? 3D rotation आपण कशा बरोबर कॅरी आउट केलं होतं? 3D rotation एक 3D ऑब्जेक्ट आहे. So I can rotate that object around x axis, around y axis, and around z axis. Okay. Up to this, is there any difficulty?
No ma'am.
Okay. Now, apart from these 3, apart from x, y, z, if I have a random axis L, if I have this random axis L and I want to rotate the object around L now, आता एक्स वाय झेड चा काहीच रोल नाहीये. आता माझ्याकडे एक ऍक्सिस एल आहे आणि मला हा ऑब्जेक्ट एक क्यूब तो एल च्या अराउंड रोटेट करायचा आहे विथ सम डिग्री थीटा, विथ सम अँगल थीटा. ओके, क्वेश्चन कळलेला आहे आता?
Yes ma'am.
Okay, so now it is the arbitrary axis L around which I have to rotate this object with angle theta. But I don't know the T matrix for rotation about such arbitrary axis. हा एक आर्बिट्ररी ऍक्सिस आहे, त्याच्याशी रोटेशन केल्यानंतरचा टी मॅट्रिक्स काय येईल ते मला माहिती नाहीये. मला फक्त टी मॅट्रिक्स एक्स बरोबरचा माहितीये, टी वाय बरोबरचा माहितीये, आणि टी मॅट्रिक्स फॉर झेड बरोबर जे आहे तोच माहितीये फक्त फॉर रोटेशन. ओके, सो what I supposed to do is I have to shift, because as the axis, our problem is what? We are carrying out the rotation about an axis which is parallel to one of the coordinate axis. म्हणजे हा एल तरी असेल जो एक्स शी पॅरलल आहे त्याच्याबरोबर तरी मला रोटेशन करायचंय, किंवा एम हा ऍक्सिस असेल जो वाय शी पॅरलल आहे त्याच्याबरोबर रोटेशन कॅरी आउट करायचंय, किंवा एन हा ऍक्सिस आहे आर्बिट्ररी ऍक्सिस जो झेड शी पॅरलल आहे त्याच्याबरोबर मला रोटेशन करायचंय या ऑब्जेक्टचं. ओके, सो हा पॅरलल आहे म्हटल्यानंतर ह्याचं डिस्टन्स थ्रू आउट सेम असणार आहे. हे जेवढं डिस्टन्स आहे तेवढंच हे डिस्टन्स पण आहे. So this distance is remaining same. Now my idea behind this is I don't know the T matrix for this rotation about this axis. So what I can do is I will shift this T L downwards. That means I will translate this L downwards so that X and L will be coinciding on each other. I will shift this axis down. Now, when I'm shifting this object down, that means shifting this axis down means this object is also moving downwards, because the whole thing I'm going to make the L axis coincident with X. In the same manner, if the axis is M, shift it in this way so as to coincide on Y. For N, it will coincide on Z axis. इथपर्यंत कळले आता?
Yes ma'am.
Okay, so first step is translation of the axis, so that translate the object and the axis so that the rotation axis will coincide with the parallel coordinate axis. मग तो x असेल किंवा y असेल coordinate axis किंवा z असेल, ज्याच्याशी पॅरलल असेल त्याच्यावर आणून coincide करतो आपण. Now once it is coincided, मग काय झालं, एल आणि एक्स आता एकच आहे. सो आय कॅन यूज दिस टी मॅट्रिक्स विच वॉज देअर फॉर रोटेशन अबाउट एक्स, बिकॉज आवर एल अँड एक्स आर वन अँड द सेम थिंग नाव. सो नाव आय कॅन रोटेट द ऑब्जेक्ट विथ रिस्पेक्ट टू एक्स बाय युझिंग द टी मॅट्रिक्स विच इज ऑलरेडी अवेलेबल. आणि मग रोटेशन करून झालं. आता या डायग्राम मध्ये बघा, हे एक्स वाय झेड आहे, आणि मला कॅरी आउट करायचं या डॉटेड लाईन बरोबर या पिरॅमिडचं रोटेशन. या डॉटेड लाईन बरोबर मला रोटेट करायचंय पिरॅमिड. Then I will shift this dotted line downward so that it will coincide on x-axis. मग ही लाईन डाऊनवर्ड आली म्हटल्यानंतर हा पिरॅमिड पण खाली आलेला आहे त्या लाईन बरोबरच. तुम्ही बघा डिस्टन्स बिटवीन द पिरॅमिड अँड द लाईन हे जेवढं होतं तेवढंच डिस्टन्स आहे आता एक्स ऍक्सिस बरोबर आणि पिरॅमिडचं. So I am making this line coinciding on the x. Then I will carry out the rotation. मग आता x आणि तो ऍक्सिस सेम आहे म्हणून रोटेशन फाइंड आउट केलं. सो आता ऑब्जेक्ट रोटेट झाला तुमचा विथ गिवन अँगल थीटा. आणि रोटेट झाल्यानंतर मात्र काय तर आपलं रोटेशन कंप्लीट झालंय. सो वी विल शिफ्ट द रोटेशन ऍक्सिस बॅक टू इट्स ओरिजिनल पोझिशन. सो हे जेवढ्या अमाऊंटनी खाली शिफ्ट केलं होतं तेवढ्याच अमाऊंटने मी परत वरती शिफ्ट करते या रोटेशन ऍक्सिसला. ओके, सो द ऑब्जेक्ट विल बी ऑल्सो गेटिंग शिफ्टेड अपवर्ड्स. इथे बघा तुम्ही रोटेशन झाल्यानंतर तो एक्स ऍक्सिसच्या पुढे डिस्टन्स बरंच होतं, पण आता रोटेशन ऍक्सिस तुम्ही वरती शिफ्ट केला की हे ऑब्जेक्ट सुद्धा अपवर्ड्स मूव्ह झालेलं दिसतंय. सो इट मीन्स द अल्टिमेट रोटेशन अबाउट दिस आर्बिट्ररी ऍक्सिस इज डन. Okay, so this is how we are going to have the steps. Now it is clear?
Yes, ma'am.
Okay. Boyd side, is there any difficulty?
No, ma'am.
Okay. So this is how we have done the rotation about any arbitrary axis parallel to coordinate axis. हा पॅरलल होता म्हणून आपण शिफ्ट करू शकलो आणि रोटेट करू शकलो. आता नेक्स्ट बिट काय आहे तर नेक्स्ट बिट आहे की आय एम गोइंग टू रोटेट द ऑब्जेक्ट around any arbitrary axis which is non-parallel to any of coordinate axis and it is in the space. आता काय होतं हा पॅरलल होता ऍक्सिस म्हणून मी रोटेट करू शकले, पण आता मला काय करायचंय एक असा ऍक्सिस आहे. सो दिस इज युअर ऍक्सिस which is neither parallel to xyz and this axis is in the space. So around this axis I want to carry out the rotation of the object. Okay, getting the difference between these two arbitrary axes. एक दोन्ही आर्बिट्ररी ऍक्सिस आहेत, फक्त एक ऍक्सिस जो आता बघितला आपण तो पॅरलल टू कोऑर्डिनेट ऍक्सिस होता आणि आता हा ऍक्सिस आहे विच इज नॉन पॅरलल टू एनी ऑफ द कोऑर्डिनेट ऍक्सिस. इट इज इन द स्पेस and still we have to carry out the rotation about this axis. Okay, okay, so what I can do for this axis? Question कळालाय सगळ्यांना की next bit काय? Yes, so that is our last bit of this chapter, that rotation about an axis in the space. Okay, okay, so you can see this diagram in which it is the axis which is in the space having x1 y1 z1 x2 y2 z2 as the endpoints, and this is the pyramid given a three-dimensional object that I want to rotate it around this axis. Okay, so how I should move? So for this particular example I will be shifting this axis such that this x1 y1 z1 will lie on origin, because We are having the rotation matrix for XYZ. आणि XYZ मध्ये common काय आहे? तर origin आहे. Right? So I have to make this X1, Y1, Z1 to move here. So that I will move that point with minus X1, minus Y1, minus Z1. Getting it, all of you?
Yes, ma'am.
Okay. So what I will do, I will shift this point here, and that is your first point, that translate X1, Y1, Z1 to the origin. So I'm going to shift this point to the origin. So first matrix is translation matrix. Right? First matrix is translation matrix. Then next step मध्ये काय होईल? आता ही लाईन आहे ती शिफ्ट झालेली आहे आणि it is somewhat like this. Okay. आता ही लाईन इथे आलेली आहे, त्याचा एक पॉइंट X1, Y1, Z1 is now origin. तो आपण origin पर्यंत शिफ्ट केला स्टेप नंबर 1 नंतर. But the second end is still in space. Second end is still in space. बरोबर, कारण ही लाईन स्पेस मध्ये. It is having X2, Y2, Z2, which is a non-zero value. जर X2, Y2, Z2 ह्या तिन्ही व्हॅल्यूज नॉन झिरो असतील तर याचं मिनिंग आहे तो स्पेस मध्ये पॉइंट. फॉर एक्झाम्पल, इफ यू आर एबल टू व्ह्यू दिस, view my hand, it is having 3 axes, right? And this plane is acting as your axis, where the plane is having one point at origin and the other point is in space. कळतंय सगळ्यांना आता? Yes? Tell me yes or no so that I can see if it is further simplifiable.
No, ma'am.
Not getting. Current, what is our requirement here? This is your with right hand or left hand, which will be easier for you to look. I don't know. Okay. So use your right hand to indicate the three-dimensional axis. So middle finger represents z-axis, the upper finger. Okay. Is it okay now?
Yes, ma'am.
Okay. So in this case, this is your 3D coordinates, x, y, z axis. And my question is, now this plane is acting as a any arbitrary axis. And around this plane, I have to rotate the object. कळलं आता questions again ना?
Yes, ma'am.
Okay. Now what I will do in the first step, I will move this pen downward so that it will pass through the origin. So origin is here, suppose. Okay. Origin is here. But whether the second point of the pen, whether the second point of the pen is lying in any of the plane, no, it is still in the space because x2, y2, z2 are non-zero values. So I can say only one end is in the origin. This is your origin. So only one end of the pen is passing through the origin, or it is having the same value as 0, 0, 0. That is x1, y1, z1 has become 0, 0, 0. But x2, y2, z2, the second end is still in space. Now it is okay?
Yes, ma'am.
Okay. So again, I don't have, though it is passing through the origin, I don't have T matrix for this pen. माझ्याकडे या पेन साठीचा रोटेशन मॅट्रिक्स आहे का? नाहीये. माझ्याकडे रोटेशन मॅट्रिक्स फक्त XYZ साठीच आहे आणि या तिन्हीलाही पेन कोइन्साइड करत नाहीये अजून. बरोबर. सो what I have to do is now I will rotate this pen on Z axis. So Z is my middle finger. So I will rotate it on Z axis. So rotation is carried out on Z. So I will rotate so that it will lie in, rotate about Z so that it will lie in XY plane now. हा पेन आधी इथे होता. Around this Z axis, I have rotated it. Now it is lying in the XY plane. Okay. आता काय झालं माझा? एक कोऑर्डिनेट मी कमी केला त्याचा. कुठला कोऑर्डिनेट? Z कोऑर्डिनेट मी कमी केलाय सध्या. Because I have rotated it with Z axis so that Z coordinate has been removed and I will have XY coordinates only. So हा पॉइंट मी रोटेट केलाय with respect to Z so that with this angle it will lie in XY plane. आता तो XY plane मध्ये lie झालाय. म्हणजे ह्या पॉइंटचा आता Z coordinate कट झाला. Only X and Y coordinates will be there with it. Getting it? Yes, students.
Yes, ma'am.
Okay. So that angle is considered as alpha angle. So rotation is carried out. Or we can say rotation is carried out about X and Y. You have to make it coincide on any plane and then any axis. That is the main thing you have to do. म्हणजे पहिलं एक रोटेशन केलं. फर्स्ट रोटेशननी काय झालंय तो XY प्लेन okay. So right. So what we were discussing, 1 second. Yes. So we have made x1, y1, z1 to coincide on origin, but as still the another end is in the space, so we are going to rotate it twice, one along with x-axis and then along with y-axis, so that with x and y rotation it will lie on z. दोन वेळा रोटेट केलं तुम्ही, फर्स्ट टाइम काय होणार आहे, हा हा पॉइंट आहे, जर मी एक्स बरोबर त्याचं रोटेशन केलं तर तो वाय झेड प्लेन मध्ये येईल. आता मी पहिल्यांदा म्हटलं होतं आपण झेड बरोबर रोटेशन करूया तर तो एक्स वाय प्लेन मध्ये जाणार होता, बरोबर. सो हिअर दे हॅव कन्सिडर्ड फर्स्ट रोटेशन अबाउट एक्स ऍक्सिस. सो रोटेशन अबाउट एक्स ऍक्सिस केल्यानंतर काय होईल, त्याला मी रोटेट करते एवढ्या अँगलनी and it will lie in YZ plane. First, we have translated this other terminal is still in the space. So with X rotation, we are going to rotate this with X axis through alpha angle. So with this angle, we are going to rotate, and so that this point will lie in YZ now. So with this alpha angle, what will happen? This x2, y2, z2. X बरोबर rotation केल्यानंतर काय होणार आहे? This y2 and z2, it will be lying in YZ plane now. So हा space मधला point आहे, तो आता या plane मध्ये येईल, YZ मध्ये. आणि once it is present in the YZ, then I will rotate it with y axis. See here, rotation about y axis with beta angle. हा alpha angle होता, so x axis बरोबरचा आहे. Then I will rotate it with y with beta angle. So हे rotation आहे, ते beta angle नी होईल. आणि beta angle नी झाल्यानंतर हा point rotate होऊन z वरती coincide होईल. So movement from space to YZ plane, from YZ plane to Z axis. आणि आता Z वर तो lie होतोय, so I can use the rotation about Z, and that's why this is your rotation about Z. So at third number step we are achieving the actual rotation about Z axis. Getting it? So first काय केलंय मी, arbitrary axis ला move केलंय, so that one point will be your origin, other point is in the space. Then carry out rotation about x and y. Rotate this x2, y2, z2. हा जो x2, y2, z2 आहे तो पहिले मी x बरोबर रोटेट केला, मग तो lie झाला yz मध्ये. Then I will rotate this also with beta, then it will lie on Z axis. And as now this xyz, x2, y2, z2 and this Z axis is coinciding, I can carry out the rotation with Z. So this rotation is carried out here. Now rotation तर मिळालं माझं, whatever the task was given, that is over. So you have to do the inverse transformations. मग पहिल्यांदा Z वरती असलेला तो परत बीटानी रोटेट करायचा, इथे येईल, that is called as rotation with beta angle. तिथून परत तो अल्फा एवढ्या अँगलनी रोटेट करायचा, so that it will come in the space again, and then translate it back to its original position, which is your T. So it is the T matrix. Okay, so total there are 7 steps to carry out for rotation about any arbitrary axis in space. Getting it?
Yes, ma'am.
Okay. So next, what we can say is the next thing, next slide is doing the same thing. Only I have drawn here the diagrams. In the slide, it is already available. Okay, so we will see the steps one by one again. So first is the translation. So this red axis is translated so that it is passing through the origin now. So the second end is still in the space. So we will rotate it with x-axis with alpha angle. So you can see now this rotations. So rotation is done with alpha angle so that it will lie in the y-z, and then again I will rotate it with y so that it will coincide on the z-axis. That is your third step. So rotation about y-axis, it will lie on the z-axis. So it is the point x2, y2, z2. And then z-axis and that point is same, and that's why carry out the rotation with z-axis. So this is the T matrix for rotation. And then translate them back to its original position. So translating back. So these are the first three transformations. Translation, rotation about x, rotation about y. Then this is a rotation about z. And then comes the inverse transformations. So inverse transformation is nothing but these x1, y1, z1 will be plus, plus, plus for t. Then this rotation angle is changing the sign values. Here it will be minus sine alpha, here it is plus sine alpha. So that is the T matrix for rotation, inverse rotation about x. And inverse rotation about y is again having this minus sign over here, plus sign over here. Okay. So this is the final T matrix for the rotation about arbitrary axis in space. Getting it?
Yes, ma'am.
Boys side?
Yes, ma'am.
Okay. So the example is given for the same. This is the arbitrary axis, A210 and B331. So around this axis, you have to rotate the cube with 90 degree. So this is the axis drawn, or rather shifted, because the coordinates are 210, 331. So 210 has reached to 000. Similarly, B dash is also moved because earlier it was having coordinates 331. From that we have reduced 210. So you will have 1, 2, 1 as the point. Yes, here you are having the 1 to 1 point after performing this shifting. Then rotation about x, rotation about y, and then finally it will coincide on z. So rotation about z is carried out with the specified angle. 90 degree rotation करायचं आपल्याला. So 90 degrees applied for rotation about z, and then inverse translation will give you this final result. Okay. So it is the example for rotation about an arbitrary axis in space. Okay, getting it? The example you can see afterwards, because the steps I have discussed, only the calculation part you can do it later. Okay, is there any difficulty here? Yes.
No, ma'am.
Okay. So this ends with your chapter number 3. And now we are going to start with the chapter number 4. I will open those PPTs for chapter number 4. Wait for a while. Okay. Whether the PPTs are visible?
Yes, ma'am.
Okay. So now let us start with the second section. First section is over. In that, unit number 4 is clipping and display file compilation. So in this chapter, we are going to learn what is the method clipping and the details about the display file compilation. So for clipping, we are going to learn 2 algorithms. Here we are having only line clipping in our syllabus. So Sutherland-Cohen line clipping algorithm and midpoint subdivision line clipping algorithm. These 2 algorithms we are going to study here. And then we are having the viewing and window transformation, and then followed by the display file. So we will see first what is windowing and clipping, because this has actually the Mhm. Okay. So what is windowing and what is clipping? So the example is, whenever we want to take a photograph, whenever we are taking the photograph of any scene in the nature, then we are taking only some portion of that whole scene. For example, this is a scene in the real world. Okay, this is the scene in the real world, and I want to take the photograph of the house. I want to take the photograph of the house. So I will take photograph, and it will be like this. Okay, it will be like this. Then I am going to take the photograph of the house. In that, I am having some portion of the tree also. I'm having some portion of the tree also. So this particular screen is called as your viewport, while the real world scene is called as your windowing. That means windowing is nothing but the things that we can observe out of the window. So it is same as that of your real world picture. So this whole scene is acting as the window for you. And viewport means the amount of or the small portion of the window scene is captured and kept in the viewport. So your screen, mobile screen will have only this portion out of the whole scene. So this whole scene is acting as a window while your mobile screen is acting as the viewport. Getting the difference? Yes, students. So real world is considered as window and the picture on the mobile is considered as viewport. So we will see what is the meaning of windowing. So windowing is nothing but the process of selecting the part of real world scene to display it on some device is known as windowing. So here we are selecting the part of real world scene. This is your real world scene. Out of that we are selecting some portion and we are placing it on some device. आपण मोबाईल मध्ये फोटो क्लिक केलेला आहे. So we are placing it on mobile. This process is called as windowing. Okay, all of you are getting the concept of windowing. In the process of windowing, we are just selecting the part of the real scene and we keep it on any device. That is windowing. Is it okay? Shall I move further?
Yes, ma'am.
Okay. Then clipping window is a rectangular window against which visibility scene is tested. So in short, this can act as a clipping window. So whatever is inside this clipping window is considered as visible and whatever which is outside the window is called as invisible. So this tree, the trunk of the tree and this portion of the tree is invisible and the house and some portion of the tree is visible. So a clipping window is a rectangular structure which will decide the visibility of the object, which will decide the object which is visible and which is not visible. Okay, which is called as clipping window. Then clipping is the process of deciding and removing the portion which is outside the clipping window. And what is clipping then? So we are having this picture as a whole, and out of that, what we are doing? We are keeping this portion which is visible with respect to the window. We are keeping it and we are removing the portion which is outside. We are removing the portion. We are cutting the portion which is outside the window. This method is called as clipping. Okay, so clipping window is a rectangular framework which decides whether the object is visible or not. And the process of clipping is removing the invisible portion. Removing the invisible or outside portion is the method of clipping. Getting it? All the definitions?
Yes, ma'am.
Okay. So what is viewing transformation, or it is also called as window to viewport transformation, or it is also called as windowing transformations. So one and the same thing. viewing or windowing or window to viewport transformation. So here the window is nothing but world coordinate area, which is selected for display. It is the window. Viewport is nothing but the display device, that is the device coordinates. So we have seen the whatever is available outside the window, the nature scene, that is considered as window, and whatever we are capturing in our device, maybe mobile, laptop, whatever we are capturing, the portion of that window is nothing but your viewport. Now, okay. So whenever I'm capturing this house on my mobile, whether the size of the house, size of the actual house and the size of image are same. Whenever I am capturing any house, then the size of the house is too big. Actual size of the house is too big, but I am getting the full picture in my screen. So that mapping is done, proportionate mapping is done rather. So whatever the shape of this object is there, whatever the dimensions of the object are there, the ratio between the roof and the door, the ratio between the roof and the wall. So this, whatever is there in the actual picture, the same ratio is mapped in the viewport picture also. Right? So you have to remember that if our screen is changing, suppose I am capturing the image for a laptop, then the mapping will be different. If I am capturing the picture in a mobile phone, then the mapping is different. Why? Because maybe laptop screen is having horizontal resolution or horizontal pixels more than the vertical pixels, but here in the mobile handset, the vertical pixels are more than the horizontal pixels. Then also the same picture is drawn here. It do not it will not cut any portion of that. Suppose I'm taking this picture on the laptop, it will appear whole, and if I am copying it in the mobile, then it will show only this much portion. Whether it happens? No. In the mobile also I am getting the same picture, but the mapping is different. I'm going to map it in the different way. So the same picture I am also getting in the mobile as well as laptop. Only the ratio of picture with the, that is the dimensions of the screen and the actual image are varying. Okay, so that is called as viewport. So we have seen window is nothing but the world coordinate area. That is the actual nature or scene which is selected for display, is nothing but your window. And viewport is the area on a display device to which window is mapped. So this window, that is the image, is mapped on the laptop. It is mapped on the mobile. So these two are acting as a viewport 1 and viewport 2. So laptop screen is acting as a viewport 1. The mobile screen is acting as a viewport 2. Getting it? What is the window and what is viewport? So window works on world coordinate system and the viewport works on the device coordinate system. The number of pixels in the laptop, accordingly it will adjust the picture. The number of pixels in the mobile, accordingly it will adjust the picture. So it acts on the device coordinate system. Getting the difference between window and viewport?
Yes, ma'am.
Okay. So the process of mapping the part of world coordinate system scene to device coordinate is called as viewing transformation or window to viewport transformation or window in transformation. So this mapping, the actual size of the house is mapped with the device coordinate system. So window coordinate system is mapped with the device coordinate system. This mapping is called as viewing or windowing or window to viewport transformation. Getting? So it is the definition that the process of mapping part of the world coordinate system to device coordinate. So mapping the same window to different viewport. So window means now in the real world hut, I am going to concentrate only this part. The roof I am not going to consider. So this is your window. This is your window. And the window is projected on viewport. Two different viewports are there. Viewport number 1, viewport number 2. So one is showing the horizontal expansion. The other is showing some vertical expansion. Just now we have seen in laptop, we are having horizontal expansion. In mobile handset, we are having the vertical kind of expansion. So there are two viewports for the same image. Image is same. Roll number 1. So a mapping is done between the image or between the window capture and it is placed on the viewport. So there are two ways how it is represented. Similarly, where to keep that picture is also different. It is placed on the left hand side on the viewport 1. In the viewport 2, it is placed on the right hand side. So mapping is done in different ways. So we are mapping the same image in two ways on viewports. Then the next concept is mapping. We have seen in mapping, the same image is used to represent it on different viewports. And in panning, we are having two different windows that are mapped on two different viewports. So here it is nothing but the roof is shown in one viewport and the bottom part is shown in other viewport. So due to panning, we are actually dividing the window and we are separating the views on the viewport. So this whole window is divided into two parts. One is roof and other is wall. And I am representing them in two different viewports. So it gives you all type of views for the window. That is the concept of panning. So it is one of the important question as far as MCQs are concerned. So in panning, whether the selected window is same or different. So in panning, it is always different. One is having the roof, other is having the wall. So we are representing two different portions on two different viewports. That is called as panning. And in mapping, we are having the same image, that is only walls are represented in two different viewports at two different locations. So that is the difference between panning and mapping. Okay. So how actually viewing transformation takes place? So viewing transformation, just now we have seen, it is the mapping of world coordinate system to, it converts it into the viewport. But before converting into viewport, it is first converted into the physical, first converted into a normalized coordinate system. So this PDC, or it is also called as viewing coordinate system. So PDC is nothing but the physical device coordinates. That is maybe mobile, maybe laptop. So it is having the physical device coordinate system, PDC. So it has two parts. First is from world coordinate system, it is converted into normalized coordinates. And from normalized coordinates, it is converted into the physical device coordinates. Okay, so it has the normalization transformation and workstation transformation. So in normalized transformation, we may have the different physical coordinate system. That is, we may use the tab, we may use the mobile, we may use the laptop. So they have the different screen resolutions, they have the different viewports. So we have to select the normalized, what we can say, the dimensions which will be normalized and which will be easier to plot on any of the viewport given. So here different display devices have different screen sizes. You can see here the different display devices have different screen sizes. They may differ in the number of pixels, they may differ in the resolution. So if we want to display a picture on the screen, device coordinate system must be independent of device, right? Whatever may be the screen, if it is horizontal, then also we will be able to see the complete picture. If it is vertical, then also we will be able to see the complete picture. So the picture should be independent of the screen size, right? And that is why it is written like this. If you want to display a picture on the screen, the device coordinate system must be independent of device, right? It should be independent of device. And this is called as normalized device coordinate system, as it is independent of the device. So what is normalized transformation? So in normalized transformation, we are going to convert the picture in unit area. So 1 unit length, 1 unit height. So we are going to draw the 1 by 1 size of the diagram, and then it is acting as a interpreter. So it is the step in between the first and final output. So whatever the picture we have captured, we are first converting it into a unit area, which is of size 1 by 1, right? 1 unit length, 1 unit height. So lower left corner is origin 0, 0. Then this will be have 1, 0. Then the right top corner is having 1, 1, and this left is 0, 1. The center is 0.5, 0.5. So we are going to convert picture into this area, and depending upon the screen resolution, further we are going to expand it according to the number of pixels or the resolution of the viewport. So what this interpreter does, interpreter converts the normalized device coordinate to actual device coordinate using the equations. So here x and y are the actual device coordinates that can be obtained by adding the normalized x and the width of actual scene, actual screen. So normalized pixels plus width of actual screen that are added to get the actual device x value. Similarly, to get the actual device y value, we are adding the normalized y value plus the height of the actual screen. So when I use these formulas, I can convert the picture into world, that is viewport or window coordinate system. So consider this particular dot that I am going to display on my screen. This dot I am going to display it on my screen. So for that, this dot is having the world coordinate system xw yw. W stands for window and V stands for viewport. So xw yw should be converted into xv yv depending upon the formula. So it has a formula for the window max y value, window min y value, then windows x minimum, windows x maximum. So it has total 4 values: x parameter of the window minimum maximum, y parameter of the window minimum maximum. So if I want to represent the lower left corner of the window, if I am having this lower left coordinate, it has xw min, yw min as coordinates. So xw min, yw min represents the lower left corner, that is bottom left corner. And if I want to get this upper right corner, then it is xw max, yw max. Same is there for viewport. Viewport la सुद्धा x min x max आहेत, y min y max आहे, which represents the bottom left corner and upper right corner. Now, in order to represent any coordinate xv, yv, what is the relation between the actual coordinate world coordinate system and window coordinate system? That is explained in the further equation. With further equation, it is represented. Okay. So the viewing coordinate minus xv minimum, whatever the ratio between these two is available, the same is there for the ratio between the world coordinate system. So it is viewport coordinate xv minus xv min divided by xv max minus xv min is equal to xw minus xw min, xw max minus xw min. So the ratio is maintained. And that's why on the small screen also we are able to view the whole home, whole house, because the ratio is maintained between the actual world coordinate system and the viewport coordinate system. So this ratio is maintained. Similar is for y coordinate. So yv minus yv min divided by yv max minus yv min is equal to yw minus yw min divided by yw max minus yw min. So these are the expressions. And in that expression, I am going to perform the multiplication here. So I am having this formula, that is the same formula earlier that we have taken. See here. So xv is calculated. So I'm going to multiply this bottom, the denominator this side. So I will have xv max minus xv min divided by xw max minus xw min. And this is in one bracket xw minus xw min. Then I will add this term. This term is minus this side. So I will add this here. So I will have xv is equal to this multiplied by this bottom term plus xv min. So that is only written over here. xv min add केले त्याच्यानंतर xw minus xw min ही पहिलीच टर्म आहे तुमची आणि त्याला मल्टिप्लाय केलंय sx ने. sx म्हणजे काय तुमचं xv max जी इकडे बॉटमला होती ती इकडे क्रॉस मल्टिप्लाय झाली आणि ही होती ती टर्म xw max minus xw min. So we are having that sx and sy which are the ratio between the viewport and window. So if sx and sy are same, sx and sy are same. So what we have seen in scaling, when sx and sy are same, uniform scaling takes place. So here also, if scaling factors are same, then proportion of the object is maintained. So if we are having the sx more, then the x dimension will be stretched. And if I am having sy more, then the picture will look vertical, right? So that is, and if both are same, then vertical and horizontal ratio is maintained. Okay, so in order to get that previous expression, we can have this T matrix. If I want to get this first and second expression, what I will have is this T matrices. You can see here xv min and yv min हे add केलेत, and that's why here you will have xv min and yv min in translating factors म्हणजे जे add होणार आहेत ते. Then scaling sx and sy ने multiply केलंय. So sx and sy are in the diagonal elements. आणि you are reducing xw min, yw min, and that's why they are here performing wx min and wy min, performing subtraction. Okay, so this is the overall transformations required for converting the window coordinate system into viewport coordinate system. Getting it? Yes, students?
Yes, ma'am.
Okay. Boys side, is there any difficulty? Boys side, all of you are getting? Okay. Okay, I got your response through chat box. Okay. So we have seen the difference between what is windowing, what is window, what is viewport, what is clipping window, what is viewing transformation, windowing transformation, and how the ratio is maintained between window and viewport. So these many things we have learned from the chapter number 4. And in the next lecture, we will be observing the clipping method. So point clipping and line clipping that we will learn in the next lecture. Okay. So for today, we will stop here. Point clipping is easy. Already you had it in your diploma, right? It is not there in our syllabus, point clipping, but the content other than syllabus, for that I have included this point clipping also. So you can just go through the slide. So clipping means what? Just now we have seen the definition of clipping. What is clipping? Yes. Can anyone tell what is clipping? So clipping is nothing but the portion which is visible. We are going to accept that portion for display, and the portion which is invisible, then we are going to reject because we are not going to display it on our screen. So with respect to this, clipping means the house and small portion of the tree is visible. So we are going to accept it for the display on our device, and the remaining portion of the tree is outside the window, and that's why we can remove that, we can clip that, or we can delete that, reject that, so that it will not be the portion on my viewport. Okay, so that is called as clipping. So if the point is inside the window, then it is observed as accepted and we are going to display it on the screen. Otherwise, if the point is outside, then we are going to reject that and it is not considered for displaying on the screen. That is called as point clipping. So here is the point clipping example. So in point clipping, if the point, if the window is having the uh, lower bottom corner, lower left corner, and upper right corner as x min, y min, and x max, y max respectively. So it represents the whole boundary of the clipping window. And P is inside. आपण कधी म्हणू शकतो P हा inside आहे या विंडोच्या? जेव्हा x coordinate is in between x min and x max and y coordinate is in between y min and y max. Right? जेव्हा x ची व्हॅल्यू x minimum and y minimum x minimum and x maximum च्या मध्ये असेल आणि y ची व्हॅल्यू ही y minimum आणि y maximum च्या मध्ये असेल, तेव्हाच we will consider the point P is inside the clipping window. So that is only the test for point visibility, whether the point is visible with respect to window or not. Okay, so this is the concept of point clipping. And if any one of this condition is failing, here and operation is required, that means both conditions should be satisfied, then only it is inside. If only one condition is satisfied, for example, x value is in between x min and x max. So this is your x min value, this is your x max value, maximum x. If only one value is satisfied or one condition is satisfied, that is x is in between x min and x max. For example, this point. What is the x value of this point? It is lying in between x min and x max. The first condition is satisfied. But the second condition, what is the y value of it? Y value is more than your y max. Y max ही value line, y max ची line ही आहे आणि y min ची line ही आहे. So your y value is greater than the y max. So second condition is not satisfied. So if I am having only one condition true, then the point is not visible or it is not inside point. Okay, if the point satisfies both the conditions, then only we are going to consider the point is inside. Else we are going to reject that point as it is invisible. Right? So you can draw these 3 points and check the visibility. Okay. So we will stop here for today. Give me attendance. Roll number 1. Roll number 1. Attendance.
Present, ma'am.
2,
Present, ma'am.
3,
Present, ma'am.
4. Okay, thank you. 4. 5,
Present, ma'am.
6, 6 roll number is not there. 7, 8,
Present, ma'am.
9,
Present, ma'am.
10,
Present, ma'am.
11,
Present, ma'am.
12, 12 is also not there. 13, 13 is present. Okay. 14,
Present, ma'am.
15.
Present, ma'am.
Okay, thank you. You can leave the meeting now.